Okay, so welcome to the second part of the fiber optic module, I would say. During the first part, we went over the basic principles on how the signal travels in optical fiber. Now we're going to take overall look on the practical applications, and the whole thing is going to be topped up or topped by the lab exercise during which we're going to perform a fusion splice. We are not going to have time to do the mechanical splice. However, Mr. Cunningham and I did a couple of years ago, we did a little instructional on that, so I will include that in our YouTube playlist. And if someone is planning to go into, into this kind of business, talk to me. I will spend some extra time after class and I will show you how to do the mechanical splice. Although with the instructional video that we did with Mr. Cunningham, that should be quite self-explanatory, and especially if you go through the fusion splice, you should have no problem. Although there is nothing like the real thing, which is the actual practical kinesthetic kind of approach, which means doing things by doing things, not just reading about them or hearing about them or just watching videos. All right. So anyways, here for you, but I digress. Now, what do we see here on this beautiful picture? We see something that reminds us of maybe the patch panel that we have studied, those patch panels. Copper. Now, this is not copper patch panel. This is a fiber optic, or the optical fiber patch panel. What do we have here? We do have like a see-through couplers, and these are the it's a coupler. Each section has a coupler here, and then you insert the connector with the fiber on one side, insert the other connector on the other side with another cable or fiber optic strand, and those couplers align the cores and the claddings, the whole links, in a way that the light signal made out of light pulses is going to travel quite comfortably. Right? So that's what we see here on this picture. Now let's All right. What we are going to cover in this class, in this session here, we'll cover three cable types, loose tube, tight buffered, and a ribbon cable. And then I'm also going to explain to you the why we actually have those carrier frequencies the way they are, okay. Why? Okay, you know what I mean. All right, it's Friday. Okay, loose tube. What's the idea behind the loose tube? Well, here are the tubes, and loosely they are strands packed in those tubes. So therefore, i.e., loose tube type of a cable. In short, now what do we have here? We have the whole jacketing, outer jacketing. We have the, water absorbing material. What is it called? Water blocking yarn right here. Dry core. This material is quite water absorbent. It's amazing how much water that thing can absorb. It can absorb a lot of water. Okay. All right. Got it? Got it. There's always going to be some moisture, and moisture is not our friend when it comes to this type of installations. So somebody had the great idea of wrapping things up with material that can absorb a lot of water. All right. This thing can absorb a lot of water. Just like those, I've seen some commercials of some sort of like not a handkerchief, but some sort of camping tissues, wiping tissues or whatever, and they were in the form of like candy drops or something like that. And you put that thing in water and it expands to be big cloth. So that type of material here. Now, why do we have a loose tube? Well, let's go back to the beginning. The fiber optic link, basically what it is, it's a core embedded in a cladding, and cladding is a surrounding, just like we studied in the previous lesson. And that's not going to change. The only thing is that you could have a choice of multi-mode or a single mode fiber. But both of them have core and they have cladding. And right now, with the fiber being produced these days, the cladding's diameter is 125 microns, and the core of a single mode is somewhere around 9 microns, and the core for the currently produced for the multi-mode is about 50 microns. It is actually 50 microns. So here we have the core and the cladding, and that's where all things had. Well, everything happens. Basically, here's the idea: the light travels through the core, bounces off the cladding, and it's being kept within the core. And here it is. That's the whole story. However, there's more to the whole story because everything else is a dress up. We're dressing this cable or the strand up to make it a cable. Well, one reason is so we could have multiple strands contained within one cable. The other reason why and how we are going to be wrapping things up, just like a gift wrapping, but it's not a gift, is how we are going to be using it, where it's going to be installed, what is it that this cable is going to be exposed to. Sun, cold, snow, is it going to be inside, is it going to be outside, and whatnot. So all that paraphernalia is to protect the signal carrying strand, right, which is core and cladding. Okay, that's it. I said that many times now. So this here loose tube, mostly, if not 100% of the time, you're going to see single mode fiber strands in there. These are the single mode fibers. These are tubes, and those strands are just loosely dropped in them. That's why it's loose tube. Why is it loose? Well, it is loose because this cable usually is installed outside, exposed to the elements. Extreme cold in the winter, extreme hot in the summer. Things contract, expand, gather moisture. Still, in spite of the material that can absorb a lot of water, still we're going to get some moisture there, right? So with all the temperature differences and all the extremes, things can expand and contract, and well, as they do expand and contract, those fiber strands can be actually crushed by that action. So the tubes are a little bit bigger, and well, they're big enough to give some wiggle room to those bunch of strands that are loosely packed in a tube, all right, to make a cable. All right. Of course, we have some thick and tough outer jackets. You can step on that thing. You can probably ride over with a car, and it should be fine. Well, don't do it. And then we have, what is that thing? The three here. The central strength member, non-metallic. In order to get well, to give us less flexibility, which results in more protection of the whole cable. These here are installed. I'm just going to skip a couple of slides and going to come back to it here. Here. Oop, come back, come back, come back. All right. They're installed here. These are the cables. See, that's the cable with the loose tube, bunch of loose tube strands in them. And they are being installed in FOSC. Here's a FOSC. Fiber optic splice closure. I'm pretty sure you see a lot of these things right now around every neighborhood, pretty much everywhere, right? What's inside that? Well, inside there are cables. These are the cables, fiber optic cables. And usually you're going to have a slack of that cable and coming back, like a loop of all the cables that are going in there. So this FOSC can be taken off the main line here, physically removed, brought down, brought into a working van with the doors, well, mostly closed. So we have nice, consistent, dry, clean environment. So the cover can be taken off and we can get at those splices of the, excuse me, I'm not gonna answer that. I'm gonna let this thing ring. And all right, let's keep going. There. Okay. So let's say, for example, this cable can go 5 kilometers that way. This cable, the other cable, can go another 10 kilometers that way, and they meet here, and some of those things can be spliced, rerouted, and whatnot. So the cable will be stripped here, prepared for splicing, and fusion splice is going to be performed just like the one that we're going to do during our lab. This is the last lab session. Okay. Also, there is a video that there are tons of videos because people do film themselves doing this kind of stuff here. This is just one of them, but if you just go on YouTube and type FOSC splicing or something like that, field splicing, fiber optic splicing, you're going to see a bunch of videos. See if that kind of a thing appeals to you, because there's, I would say there will be a lot of jobs doing that. They are already, right? Okay. Let's go back to where we were. All right, so that was the slide here. Now there's certain details, and I'm giving you more detail on this thing than you actually need to know. But if you are interested in knowing a little more, then here is the information, and you probably know how to go about it. It's a good start. All right, here is this slide here is polyethylene versus PVC and that type of insulation, what this thing is good for, and so on, because those materials are going to be used producing the jacketing, inner jacketing and outer jacketing of the fiber optic cable. So at least you know some characteristics of that. I'm not going to test you on that, but I might ask you what a thixotropic jelly is. Because those loose tubes sometimes are also filled with jelly, and that thing is sometimes filled kind of smidged with jelly all over the place. With a thixotropic jelly. Thixotropic jelly is basically jelly or gel that is supposed to keep its consistency, physical consistency, when exposed to extreme temperatures, hot or cold. Right? All right, let's keep going. What's that? Okay, here's that thing. Yeah, thixotropic fluid is one that takes fixed time to return to the equilibrium viscosity when subjected to abrupt changes in shear rate. Well, in other words, the liquid becomes less viscous, thinner, or flows more easily When shaken, stirred, agitated, and otherwise stressed, the fluid then recovers to its original viscosity in a fixed time once a shear load has been removed. So it's has to do with the temperatures and shakes and the physical abuse of that. All right, so there's a bit of protection for those cables. All right, loose tube. Where do we install that? How do we use it? Okay, designed for harsh environmental conditions in the outdoors. Fiber strands floating loosely in the designated rugged tubes here. All right. Material contraction and expansion due to temperature changes will not affect the fiber strands. These are fragile fiber strands because, and then they have a lot of wiggle room. So when everything expands and contracts, it does have some play in order not to get damaged physically. Right? Used mostly in outdoor long haul installations. Well, remember when we talked about the longest link that we can ever have in Ethernet, which is copper, which is the Cat5e, Cat6, Cat7, whatnot. 300 feet is the longest link that we could possibly have. All right. Now, here's up to 120 kilometers with the single mode fiber. All right. So, well, needless to say, you are not going to see multi-mode fiber here. Okay, you're going to see single mode because single mode fiber is the one that can carry signal over long distances. Right, we already have seen this slide. Now let's go back. Let's continue with the something that's as opposed to loose tube. Let's go tight buffered cable. All right. Okay. So what do we have here? Oh. Come on. Switch. I was going to zoom in a little bit. Here we have the fiber strands with the core and the cladding and with the buffer. So tight buffer. These are packed quite tightly, those strands, and they are protected on the outside. Well, on the inside outside, or the outsider inside, in the middle, right? With the armored yarn, very tough, silky like strands. It's Kevlar. Kevlar also is used to produce bulletproof as the active component of the bulletproof vests. Right, so this thing is tough, and it's packed. The whole thing is packed tightly. The silkiness of the Kevlar gives a nice, beautiful feeling of flexibility there, right? So this, as opposed to a really tough and stiff and rugged loose tube cable that is supposed to go outside, exposed to all kinds of physical elements, then this thing here is to be installed inside, within a LAN environment. So you would run these cables between the closets, or you could also use this type of cable in as a patch cords, the patch connecting cords for the fiber optics. Mostly you're going to see this within the multi-mode because things are being multi-mode is less expensive. The multi-mode fiber can use LED as a transmitter to transmit the light. LED is less expensive than a laser source, light source, which has to be employed within the single mode. So it's all about money. If I think that if money was no object, then by now chances are that we would be running all single mode fiber and equipment. But if you don't need the capabilities of the single mode, if you are running the wire within the LAN environment, within the building environment inside, And if it's going to do more than you ever need, then why go overboard and install single mode while this thing is being installed single mode, I mean, between cities and so on, or within the city. Now, it tells us that this is a multi-mode. Right away, we can see that this is a multi-mode cable because of this outer jacket. The outer jacket is orange, which means it is a multi-mode cable, or this cable contains multi-mode fiber optic strands. Okay. Now, I gotta zoom out before if I can change slides. All right, tight buffered cable. Designed for indoor applications, fiber strands packed tightly within the armed yarn and wrapped with an outer jacket. It was way more flexible than loose tube cable, but also more fragile because of that. Used mostly indoors in LAN environment, local area network. All right, like for example, here. And then again, look at this. These are yellow patch cables, which means that looks like it's a single mode. Orange would be multi-mode, yellow would be single mode, and then there's aqua. Okay, we'll get to it. Aqua is like a blue type of, and then these are blue cables. These are the Ethernet cables here. So this looks like here, these devices, these modules here, this would be a single module like that. Transmit, is it transmit? Receive. Oh, and look at that. What do we have here? Ethernet. So remember when I was talking to you about some device that's called a media converter? Well, this would be a media converter right here. One, here's another one, here's another one, and here's one that has nothing plugged into it. Okay, so that's what the fiber optics. And here's some more optical fiber couplers maybe or something that are not being used. All right. Now, here's sort of like a loose tube, but it's a ribbon cable. Somebody discovered that if you arrange those fiber strands in this sort of way, you make ribbons out of it. So here's one ribbon, here's another ribbon, here's another ribbon, and so on. So this one has 1, 2, 3, 4, 5, 6 ribbons, and each contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I knew that. So that is a lot of strands. You won't be able to fit that many strands. Well, 12 times 1, 2, 3, 4, 5, 6. Let's just see here. 12, whoops, 12 times 6. Oh, that's 144 cable fiber strands. All right, right here. 144, 144, 144. Oh, wow. In one cable, that's a lot. This thing can service a couple of neighborhoods. That's a lot of fiber. If you arrange those in the ribbon, you get some benefits. You can pack safely because they fit better. More of those in single tube, so you can carry more strands. And also, if you have a ribbon, the fusion splicer that we're going to use is capable of splicing one strand at a time. Well, two, because you're splicing two strands so they can be joined, but it's a single strand splicer. There are also way more expensive fusion splicers that they can do the whole ribbon at once. Boom. Instead of one by one doing the splice, you just put in the whole ribbon from one side, whole ribbon from the other side. Boom. The whole ribbon is spliced. So sometimes it is okay to do that, and sometimes you can't do it because you're connecting different things to different places. So installation, when it comes to ribbons, installation also is much easier. And identification of those cables or those strands is much easier as well. So that's the whole thing about the ribbon. ribbon. Let me, okay, what's happening here? Okay, settle down, settle down. Computers. All right, so ribbons have color code. Remember when we had 25 pair color code for the copper wires? The fiber optics also has its own color code, and I'm not going to ask you to remember that. If you are working within the business, if you get yourself a job, and if that's what you do, this color code was going to come to you. It's going to sit in your brain no matter what, whether you want it or not. So I'm not going to ask you to remember these colors because at this point it's pointless. However, I want you to know that the color code exists. And if you want to know what it is, you can Google it. But now you can Google it. Why? Because you know that it exists. Or you can look at these notes here that I'm giving you. All right, so this is the color code. Blue, orange, green, brown, slate. Reminds you of something? These are the fiber strands. And then there's white, red, black, yellow, and what is this thing? What do they call it? Violet here and rose. I don't see much difference. I know there's a difference, but if I just had just a single, well, I wouldn't be able to. It's violet or rose. Some people can, I suppose, right? Women can see a lot more colors than men, supposedly. I don't know. I never was a woman. So then if we go to 12, we kind of run out of colors. And, well, we just repeat them, adding stripes. Black stripe, You just can't add black stripe on the black strand. So the black one here is kind of reversed with you get just a white stripe on the black one, and then we continue adding the black stripe. So this is a color code for 24 strands of fiber for the fiber. All right, jacket. So these were the color codes. These are the colors for the. Using the mouse wheelie. These are how you number the strands within the ribbons. Or if it's a loose tube, then it's just strands that are just loosely thrown in there. Okay, so these will be the colors of the strands. Now here is the color for the outer jacket. Notice orange or multi-mode. See the OM? Optical multi-mode 1, optical multi-mode 2. As time progressed, the technology was improving. So this OM1 was developed earlier than OM2. And OM2 was developed earlier than OM3. That's how, optical multi-mode. Hey, we got a good cable. Well, a couple of years later, we can make a better cable. Yeah, it's worthwhile. Let's make it. Let's call it OM3. That's how it works. So orange jacket, outer jacket, and the aqua, this is called aqua color, are all multi-mode. Then the yellow jacket, single mode. And of course, same as the idea of optical multi-mode. Here's optical single mode. There we go. So this is the non-military, which would be commercial, residential, industrial, or whatnot, color code. We also have the military color code, but not going. No, I just want you to know that it exists. We're going to concentrate on the non-military, but if you end up in the military, in the army, and then if you end up doing this stuff in there, then you're going to get some additional training for sure. Extensive additional training. Okay. All right, so that's the color code for the jacketing. Now, as far as the core versus cladding diameter. Okay. This is the size of the core, the diameter of the core. This is the diameter of the cladding in micrometers or microns. Notice pretty much all across the board, the cladding is 125, it's 125 microns. Some of the earlier versions and some of the military ones, the cladding is a little bit thicker, but that's an oddball, almost kind of a thing. And then the earlier multi-mode fiber would have 62.5 microns. It still exists because fiber doesn't deteriorate, it doesn't corrode, it doesn't, well, there's no any biological process going on. It's glass. It can last many, many years. So some of the installations are still active that were installed in like 1970s. They used to use the multi-mode for 62.5 microns. You're going to see less and less of those, but still you're going to see some. The newer one, the size of the diameter, the size of the core, the diameter of the core will be 50 microns. And of course 125 microns for the outer jacket. Optical single mode, it can go as low as 5 microns, but typically it's about 9 microns. Of course, you have to, whenever you're doing installation, you're going to have to pay close attention to the specifications of the equipment that you're going to use and so on. And the equipment will tell you what it wants to be connected to. All right, so remember this. I hope you remember that. You still probably have it. This is the copper specifications. Oh, I made that in 2019. Cat5, Cat5e, and so on. Cat5 is obsolete. So Cat5e is still going strong. Cat6 is way more being popular, but it will never take over, because if anything, Cat6a will take over, but Cat6a is much bulkier and more expensive and whatnot, so that's why Cat5e is still going strong, because Cat6 can't carry 10 gigabits per second up to 300 feet. So if you only have the 1 gigabit after 180 feet, then might as well get. So that's why Cat5e is strong. But my point is, the longest you can get out of Ethernet type of a cable is 300 feet. And here are 100 megabits per second, 1 gigabit, 10 gigabits, and so on, 40 gigabit. Well, look at the 1 gigabit and maybe 10 gigabits if it's Cat6, if it's less than 180 feet, end-to-end run. 1 gigabit, 10 gigabits. Let's see here. This is the sort of a similar chart, but for the optical fiber. 10 gigabits is a lot now, 1 gigabit. What do we have here? 100 megabits, 1 gigabit, 10 gigabit, 100 gigabit. Well, sort of within the neighborhood when it comes to multi-mode. It'll be sort of the higher end of the copper. Quite in the neighborhood, sometimes some of them way bigger, 100 gigabits. Oh, that's a lot. All right. But what do we have here? Here we have the length of the link, or how far the signal can travel within the optical fiber. See this? Copper, 300 feet. Fiber multi-mode, 2 kilometers. 1.5 kilometers. 1,000 meters, 1 kilometer. 500 meters. 300, this is not feet. 300 meters. This here is 300 feet, 100 meters. Okay, so here that, okay. All right, so now, what do we have here? OM1, 62.5 core. It can go, now, okay, different sources are going to give you different information. So, but we have to have some sort of, not a start, not as like it's better than nothing. We get some approximate values here. All right, so let's say 2,000 meters, this specification sheet provides 62.5 up to 2,000 meters. And what is the speed, transfer speed? Here's the other thing here. We can travel along that. It is 1 gigabit per second. Oh, it can go 1 gigabit per second. What's 1 gigabit per second? 1 gigabit per second. That's Cat5e. Right? But Cat5e can only go to 300 feet. This can go 2 kilometers. And that was the low end of the optical fiber. Because that's the OM1, right? OM2 can go 100 megabits per second up to 1.5 kilometers, 1.5 kilometers, which is way more than we need, because this would be used, within the LAN environment to connect closets together, panels, switches within the LAN. Frames, so it will be IDF, intermediate distribution frame, having a bunch of copper connections, connected to a fiber media converter, and that then can convert with a couple of strands. Whoa, there, maybe 80 computers or so. It can connect with a couple of strands right to the main distribution frame. So it's the distance that counts with this one here. And later on speed as well, because if you go 10 gigabits per second, OM3 and OM4 can carry 500 meters, 0.5 kilometer. Within mediocre size type of a business, factory or plant, 0.5 kilometer is a lot. You can do a lot with a 0.5 kilometer. You can comfortably connect things with a 0.5 kilometer length of a cable. There you go, see here. Then here is the 100 gigabits. OM3 can carry 100 gigabits, but a little over 300 feet. This is 100 meters. Still longer than Cat5e or Cat6 or any Cat cable. So this is just the OM. This is multi-mode fibers. And here, see this? I bet you didn't notice that. Here's OS1 and OS2, which is the optical single mode that the OS stands for. And it just continues as if it was, as if it were endless, okay? From what I heard, from what I know, the equipment hasn't been invented yet to choke the single mode fiber. So then the whole thing just opens up. You're talking 100 kilometers or so. And the bandwidth, who knows? All right. As a summary for this part, and there's a second part here, we're just going to, we still got a few minutes. We're going to get to the end of this one. Single mode cable is a single strand of fiberglass with a relatively narrow diameter, according to some sources, 9, typically 9 microns. So that's a single mode. Usually it has one mode of transmission that propagates the wavelength of one mode transmissions, which is the one single light beam. 1350 and 1550, okay. 1310 and 1550. Look at these wavelengths. Remember, I showed you the last time. Sorry, last time I showed you the wavelengths that the optical fibers are utilizing to transmit the signal and receive the signal. And today I'm going to tell you why those specific ones. There's another one a bit lower here. This basically is what I just said yesterday and today. You're welcome to read that, go over it. Go ahead, and you're just going to find what. So this is just some overall statement, summary of what we have already have done. Now, maybe I should go over some of that stuff. Usually it has one mode. Okay, then on the account that there will be a little light reflection from as the light passes the single mode fiber core, meaning ideally the light would travel in an ideal straight line. Okay, so if it's a single mode, we're assuming that the light travels here, but what this thing here says is that yes, it's going to have a little bit of a slight kind of a wave just to keep it inside, but it's still going to be considered as a single straight light beam or mode. Consequently, it will reduce the fiber attenuation. Okay, so single mode will attenuate way less than multi-mode, because, well, first of all, we use laser, not LED. Optimizing speed and transmitting signals. Meaning transmission distance is a significant performance advantage of a single mode versus multi-mode. So the distance is the kind of a breaking factor. All right, single mode fiber is usually used for long distance single transmission. Right. In a nutshell, connectors. These two and these, well, this type of connector and this type of connector here. Here's an SC, stands for subscriber connector. This is the AC connector. I will show you some of them during the lab. We'll show you them. And this is, well, relatively small, but it could be smaller. Why could we use smaller connectors? To conserve space. You have all this bulky thing around it. It's actually quite small, but still bulky in the fiber optic standards. So then somebody said, okay, well, I want to just make a smaller one. LC. I think it stands for like lucent or something like that. Something to do with the luminance, like light luminescence or something like that. So LC, here's SC and LC. SC, these are the older connectors. Well, still current, but not as young as this one. LC is a smaller, newer, and it's a smaller connector. Why? So we can pack more connectors into the equipment rack. And some of the data centers, they use like a lot of that. So it's actually that important, that significant. Here is a ferrule. Here's the housing. That's it. Ferrule is the whole channel that the light actually comes through. So ferrule, like the inside of a pencil, is a ferrule. Right? Light comes out here, or is being received through here, and in this mechanical connector, the mechanical connection happens when the fiber is being nicely cut or cleaved, brought into the funnel-like entrance of the ferrule, guided into position so the light can be transferred from the ferrule to the fiber optic, nice and easy, with the index matching gel. So there's index matching happening there, just so the light can pass more easily from one medium to another. And that's pretty much it for that one. The laws, the general typical signal laws on terminating fiber with this connection. So on the connector, there will be about typically half a dB loss. What does that mean? Half a decibel. When it comes to power, was it light? Was it sound? Is it whatever? If the power is lowered 3 decibels, it is lowered, the power is cut in half. If the power is doubled, then we are raising it by 3 dBs. 3 dB, 3 decibels. So, if we have speakers pumping 100 watts of music, raise it 3 dB, you got 200 watts. Raise it 3 dB, you got 400 watts. Raise it 3 dB, it just doubles. Same goes the other way. Lower it 3 dB from 100, we have 50. Lower it, it's going to 25, then 12 and a half. Okay, so that's how the logarithmic scale works on that. So the typical signal loss on the transmission, on the signal loss on the insertion of the fiber onto the mechanical splice in this connector, typically half a dB. Fusion splice is another story then, because in fusion splice we get almost 0 decibel loss on the splice. But that's fusioning is joining actually 2 strands of wire by the means of heat. Now here's the ST connector, straight tip connector. It's not the newest. You're going to probably see that in some of the old and sometimes obsolete installations. Okay, let's go to the wavelengths. All right, I'm gonna go skip a couple of slides and come back to them. When the light travels in the glass, there could be some glass particles, or maybe some moisture particles. Sometimes the light will hit the particle and it's going to scatter all over the place, which means the sharpness of the signal is not going to be as on the output of the transmitter. Here is the line. Here, the purple line, the violet line, right here, the dotted line, is scattering. That represents a scattering. And it's put against the wavelength and attenuation. Attenuation is bad for signal because that's the signal getting weaker. As we go up with the wavelength, which lower frequency, then the scattering gets less and less and less and less. Now what are these two here? So it's absorption put against the frequency or the wavelength. Here is 850 nanometers, 1310, 1550, around that. So this is around that, this is around that, this is around that. That's where we want to have the light being transmitted through the fiber optic glass strand. Somewhere between these two frequencies, there's going to be a frequency where the light is completely absorbed, which means you shine the light on one end and you don't see it coming out on the other end. The light is absorbed. So why, you can't transmit the signal, so those areas have to be avoided. So that's why we have those 3 typical frequency lengths, or the wavelengths. As technology progresses, the fiber optic industry is implementing other means of producing optical fiber. They actually did develop technology that is not as widely implemented yet, that actually eliminates most of the water particles, because water particles in the fiber, no matter what, they're being trapped. No matter how high-tech lab you're going to have to produce the glass, there's going to be always some moisture in the air. So there's technology being developed for zero water cost. These are called water bands. Here's a water band, here's a water band. So the idea was, and it is, and it's been done, to come up with reduced water peak. So those are pretty much almost non-existent. Or zero water peak fiber, which eliminates those, in which case you can just go use any of the frequencies, as long as maybe you want to keep kind of towards this end here because you get less scattering happening, so the cleanest signal will be somewhere here. But never mind this. Still, it's pretty darn good if you have an 850, even though with that scattering there. You just can't have, frequencies high enough. Or high enough. High that would actually the scatter would deteriorate the frequencies or the signal. Right? So that was water bands. Now, attenuation, of course. Attenuation happens everywhere. Signal travels on its own, and as it travels, it gets weaker and weaker and weaker because he has to overcome the density of the medium. Still, light does too. So it's just like resistance to copper. So these are the three things that need to be considered while we're installing or using the optical fiber. So now you know what the water bands are. Now you know also why the three typical frequencies are being used. And here, I'm just going to leave you with that. There are some organized data. Primary transmission wavelengths, 850. See, this one shows 1310. The other one 1300. So around that. 1550 nanometers. And that's why, because of scattering and absorption. Industry implemented plastic optical fiber. There's also plastic optical fiber. Multimode graded index. Graded index. Okay, we have to finish this class, but please remind me to explain to you what graded index is. Graded index. And if you're watching this thing like 2 years from now and you can't find the next class or next lecture, just research that on your own. Graded index. Why do we actually have that? And here's the typical frequencies or wavelengths. And here's a single mode. And so here's multimode, single mode. Typical wavelength frequencies. Is that the last slide? Yes, it is the last slide. Okay, cool. All right, this was March 15th, 2024, and this is going to be the St. Paddy's weekend. So please enjoy the festivities. Don't do something that you wouldn't write home about, and come back nice, clean, fresh, and safe so we can continue next week. Have a good one, guys. Thank you so much.